Hello and welcome back. Well, student, in the last class, we were just talking about the oxides of 15th group elements. And in that, I told you that nitrogen form large number of oxides, whereas rest of the family members, they commonly form trioxide and pentoxide. So in today's class, we'll see these oxides. So first, we'll talk about, or I'll say it, point A, oxides of nitrogen. In this, first we'll do nitrous oxide. Nitrous oxide, the formula is N2O. And as far as the method of preparation is concerned, if you have ammonium nitrate and you heat it, it will undergo decomposition to give you N2O plus 2H2O. Let us have a look at the structure of this compound. It is N, triple bond N, dative bond O. This is a gas, and this gas is very commonly known as laughing gas. So it is used as a local anesthesia, and it is also used as a power fuel. Second, we'll see nitric oxide. Nitric oxide. Or we can say nitrogen monoxide, that is NO. Nitrogen monoxide. We'll see its method of preparation. If I react NaNO2, 2 moles of NaNO2 with 2 moles of FeSO4 in the presence of H2SO4. So in the presence of H2SO4, that is it will give you Fe2SO4 whole thrice plus 2 moles of NaHSO4 plus 2H2O plus 2NO. Well, as for this nitrous oxide is concerned, we generally obtain it in a dimeric form. It generally exists as N2O2 because it has a prominent dipole-dipole attraction. Suppose I have got N, then I have O. So where O is negative, N is positive. I have N, O. Again, O is negative and N is positive. So there is a prominent dipole-dipole attraction due to which it generally exists in dimeric state. After nitric oxide, third we'll say dinitrogen trioxide. That is N2O3. Dinitrogen trioxide can be obtained by the reaction of nitric oxide with dinitrogen tetraoxide. So that will react with N2O4 to give you 2 moles of N2O3. So this is how we can prepare it. Let us have a look at the structure of this compound. You have nitrogen, then single bond oxygen, then nitrogen. Then you have double bond oxygen along with lone pairs. So this is how this compound is. Next one is dinitrogen tetraoxide, or we can call it nitrogen dioxide, N2O4. We can call it nitrogen dioxide, that is NO2. It is this NO2 that undergoes dimerization to form N2O4. Let us have a look at the structure of NO2. Well, in this case, nitrogen has got, in ground state, nitrogen has got two electron in the S and 3 unpaired electron in the P. So due to these unpaired electron and the paired S electron, nitrogen forms some bonds. See, it forms this double bond by these two unpaired electrons. These paired electrons, they are donated to oxygen to form coordinate bond. So in this case, this nitrogen is left with an unpaired electron. In this double bond, one of the bond is sigma and the another one is pi. Pi bond is a weaker bond. This electron generally jumps into this bond, pi bond. So one of the unpaired electron comes out to oxygen. That electron again jumps into the bond and it comes out to its original place. So this transition of electron keeps on happening. And for this transition, the electron absorbs light of a particular frequency from white light. As a result of that, if we talk about NO2, it appears brown. So it is the brown gas. Brown gas. Since it has got an unpaired electron, that's why it is paramagnetic. In this compound, you are seeing odd electron bonding. And due to this odd electron bonding, it is paramagnetic and brown colored. Many a time these NO2 molecules, they undergo dimerization. So you get an equilibrium mixture of that also, like nitrogen here, then you have double bond O, coordinate bond O. This is the unpaired electron you have got. Another nitrogen, same type, coordinate bond O, double bond O. So this is N2O4, and in this N2O4 there is no unpaired electron. That's why it is diamagnetic. It is diamagnetic. Since it does not have any odd electron bonding, that's why it is colorless. Colorless. Dear students, you might have done the test for nitrate ions in salt analysis, and when you put H2SO4 into that, you see some brown colored gas coming out. That is NO2. Because of the unpaired electron that is present in it, it is brown colored and it is paramagnetic. This unpaired electron very readily undergoes pairing with another molecule, so NO2 very readily undergoes dimerization. So if you have got a dark brown colored NO2 gas, after some time it becomes light brown because some of the molecules, they will undergo dimerization to N2O4, which is colorless. That's why the brown color fades after some time. It becomes light brown after some time. So this is dinitrogen tetroxide. After that, another one is dinitrogen pentaoxide. Dinitrogen pentaoxide can be obtained by the decomposition of HNO3. So 4 moles of HNO3 when heated with phosphorus, it will give you N2O5. So HNO3, which is a good oxidizing agent, can oxidize phosphorus, or if you have oxide of phosphorus like P4O10, that will also undergo oxidation with the HNO3, and you'll get compound like 4 moles of HPO3 along with N2O5. You'll get 2 moles of N2O5. Now let us have a look at the structure of N2O5. It is very similar to N2O4. Here you have nitrogen, coordinate bond to oxygen, double bond to oxygen, then a single bond to oxygen, and double bond to oxygen, coordinate bond to oxygen. So this is what dinitrogen pentoxide is. And this is all about the oxides of nitrogen. We'll see oxides of phosphorus. So B point is oxides of phosphorus. Well, phosphorus very readily forms 2 types of oxides, that is trioxide P2O3 and pentaoxide, that is P2O5. But these oxides, they generally exist in dimeric state. So here you will have P4O6 and here you will have P4O10. So let us have a look at the structure of these oxides. Now suppose here you have phosphorus, then it is attached to oxygen like this. We call it cage-like structure. So this is P4O6. Likewise, if I talk about pentoxide, the structure is like this. Or phosphorus in this case are exhibiting +5 oxidation state. So this is P4O10. You know very well that oxides and hydroxides of non-metals, they are acidic in nature, whereas oxides and hydroxides of metals, they are basic. Since this is oxide of a non-metal, on dissolution in water, it will give me hydroxide of non-metal, which will be acidic in nature. So if I react it with water, say I am reacting it with H2O, I will get 4 moles of H3PO3. That means here I will have 6 moles of H2O. Likewise here also, if I reacted with 6 moles of H2O, I will get 4 moles of H3PO4. So these are the two class of oxoacids, very common oxoacids exhibited by phosphorus. This one is phosphorus acid, that is orthophosphorus acid. Whereas I'm writing orthophosphorus acid. Whereas this one is orthophosphoric acid. So we have orthophosphorus acid and orthophosphoric acid. So now we'll be talking about the oxoacids and of phosphorus, their structure, their acidic character. Now let's have a look at these at the structure of these oxoacids. Many a time questions they are asked give reason why hypophosphorus acid is monoprotic. Let me tell you, hypophosphorus is what? That is H3PO2. It is monoprotic. That means it gives only one H positive ion. Whereas phosphorus acid, orthophosphorus acid is diprotic. That is, it gives two H positive ion. The first one is hypophosphorus, whereas the second one is orthophosphorus. Third one is phosphoric. I'm extremely sorry, you have a lesser hydrogen than this. Here you do not have 3 oxygen, in fact you have 4 oxygen. So this is triprotic. That means it will give 3 H positive ion. This is orthophosphoric acid. Hypophosphorus is monoprotic, orthophosphorus is diprotic, and orthophosphoric is triprotic. Although all of them they have got 3 hydrogen. The answer lies in their structure. Let us have a look at the structure of hypophosphorus acid. It is like this. This is hypophosphorus. This is orthophosphorus. phosphorus. And the last one is orthophosphoric. Well, here let me tell you one thing, that the hydrogen which is attached to phosphorus cannot be donated as H positive ion. Phosphorus is not so electronegative that it can withdraw electrons from hydrogen and will release hydrogen as H positive ion, whereas oxygen is. So in the first compound, you will see how many OH group you have got, only one. So in this, oxygen will withdraw electron and donate one H positive ion. That's why hypophosphorus acid is monoprotic. In the second one, that is orthophosphorus, you will see two OH group. So it is diprotic. It will donate 2 H positive ion. In the third one, you will see 3 OH group. So it is triprotic. So the number of H positive ion donated by an oxo acid is equal to the number of OH group it has got. So here in hypophosphorus, you have got only one OH group, so it is monoprotic. In orthophosphorus, you have got two OH group, so it is diprotic. And orthophosphoric has got 3 OH group, so it is triprotic. Whereas if we talk about the reducing character of hypophosphorus acid is prominent, because the hydrogen which are attached to phosphorus can be donated as H2. So it is a good reducing agent. Although it is monoprotic, but it is a good reducing agent. In orthophosphorus acid, you will see only one hydrogen is attached to phosphorus, which can be donated as hydrogen H2. So it is slightly less reducing reducing agent, or less prominent reducing agent. So reducing character depends on the number of hydrogen directly attached to the phosphorus, whereas the proticity or the number of H positive ion donated, or basicity very commonly we call it, depends on the number of OH group they have got. Now if I heat 2 moles of phosphoric acid, if I heat it, 2 molecules of phosphoric acid will lose a water molecule and they will undergo dimerization. So I will get a dimer like this. From here, it has lost one H2O molecule. Such a dimer is known as pyrophosphoric acid. Pyro means heat. So this is the acid which is prepared by heating phosphoric acid. This is pyrophosphoric acid. This is all about their oxides and oxo acids. And please do remember these questions. Why hypophosphorus is monoprotic, orthophosphorus is diprotic, and orthophosphoric is triprotic. Now we'll move on to the next topic. And in the next topic, we have some compounds of nitrogen, which I'm going to teach you here. Like first we'll talk about nitrogen. Nitrogen gas. How this nitrogen gas it is prepared? Well, nitrogen can be prepared by heating ammonium chloride with sodium nitrate, that is NH4Cl plus NaNO2. If I heat them, I'm still sorry, Na has not come. NaNO2, sodium nitrite. If I heat it, I will get nitrogen along with H2O and NaCl. So one of a very common method, ammonium chloride you heat it with sodium nitrite, and you will get nitrogen gas along with water and NaCl. Or a common one is decomposition of ammonium chromate, that is NH4 whole twice Cr2O7, ammonium chromate. If you heat it and you decompose it, you will get nitrogen gas along with 4 moles of H2O and Cr2O3, chromic oxide. So this is how you can prepare nitrogen gas. The third method, see this one is a very important one, and I'm telling you another method that again is a very important one, that is by decomposition of barium azide, that is BaN3 whole twice. If you heat it, it will undergo decomposition to give you barium plus 3 moles of nitrogen gas. So this is how you can prepare nitrogen. Well, as far properties of nitrogen are concerned, they are not so important. You know very well that nitrogen reacts with a large number of metals and non-metals to form their corresponding nitrates. It can react with lithium straight away to form Li3N, that's a covalent nitride. Nitrogen is very commonly used in the manufacturing of ammonia. It reacts with hydrogen to form NH3. It reacts with oxygen in Oswald process to form nitric oxide, which on reaction with water gives you HNO3. So these are some general properties of nitrogen. Only preparation is important, otherwise these properties are very general. After this, we'll move on to the next compound, that is Nh3 ammonia. First, we'll see the lab method of preparation of ammonia. You can prepare it by reaction of ammonium chloride with a base. Generally, we take calcium hydroxide. On heating, it will give you 2 moles of NH3 along with calcium chloride and 2 moles of H2O. The other method can be decomposition of ammonium sulfate, NH4 whole twice SO4 plus 2 moles of NaOH. That will give you 2 moles of NH3 along with 2 moles of H2O plus sodium sulfate, that is Na2SO4. So here again you are getting ammonia. These are the lab method of preparation of ammonia. Next I am telling you the industrial preparation. This is the method for which Haber's got a Nobel Prize. In this we generally react N2 in the gaseous state plus 3H2 in the gaseous state in the presence of iron and molybdenum will give you 2 moles of NH3 in the liquid state. Here iron is a catalyst and molybdenum is a promoter of that. The NH3 which is prepared, which is obtained, is continuously removed from the container because the reaction is reversible. In order to maximize the yield of ammonia, the temperature has to be high and the pressure also has to be high, so that association occurs quickly and more nitrogen and hydrogen will get converted to ammonia. This is the method of preparation of ammonia. After this, we'll see the properties of ammonia. Well, if we talk about properties of ammonia, ammonia is slightly basic in nature. So if you dissolve ammonia in water, it will very readily give you NH4OH, which dissociates to give you NH4 positive plus OH negative, but it's a weaker base. So ammonia is a weaker base. When it is dissolved in water, it increases the concentration of OH negative ions. After this, we'll see its reaction with some of the metals like with copper and with silver, in fact with copper and silver chloride. So if you got Cu2 positive ion in the aqueous medium, as you know they are slightly blue in color, and you add ammonia to that, that will form Cu NH3 whole 4 2 negative complex 2 positive. In fact, because ammonia is neutral, this positive charge belongs to copper. Ammonia is a neutral ligand, so 2 positive charge you have got which belongs to copper, and this is a deep blue colored compound. Deep blue colored compound. Likewise, if you react AgCl with ammonia, you will get compound like Ag NH3 whole twice Cl. AgCl is white PPT and this is colorless. Once again, let me repeat it. Cu positive ion in aqueous medium, they are slightly, very lightly blue colored. But when you add ammonia to them, they get converted to their coordinate compound, which is deep blue in color. Likewise, silver chloride, if we talk about silver chloride, you have white precipitates of AgCl. If you add some ammonia into that, these AgCl precipitates will dissolve in the test tube and they will form a colorless solution, which is a coordinate compound and an ionic compound. So this is the reaction of ammonia with the copper and silver chloride. Next we'll move on to another compound, that is HNO3. Third is HNO3. Nitric acid, you know very well. Well, as far the preparation is concerned, this reaction is quite common. You have used this reaction in organic chemistry. In 16th group also you will use it. In halogens also you have used it in the preparation of HCl. What we generally do, we take a salt like NaNO3, sodium nitrate, and you reacted with H2SO4. That is the active proton donor. So it will lead to the formation of Na2SO4 plus 2 moles of HNO3. This is how you can prepare it in the lab. Otherwise, if we talk about industrial manufacturing or industrial preparation, in that we generally heat ammonia in the presence of oxygen, and along with catalysts like platinum or ruthenium. It will give you 4 moles of nitric oxide plus 6 moles of H2O. This nitric oxide on dissolution in water after its oxidation will give you nitric acid. So first what will happen? NO plus O2 will give me 2 moles of NO2, and this NO2 plus H2O will give me HNO3. So we can balance it if we want. We can write it like 3 moles of this. So that will give me 2 moles of HNO3 plus NO, which can be recycled. So this is how we get HNO3. Well, HNO3 is quite a strong acid. So if we have a look at the properties of HNO3, HNO3 on dissolution in water very readily gives us H3O positive plus NO3 single negative. So it is quite a strong acid. It is a good oxidizing agent also. So it has a tendency of reacting with more maximum number of metals and non-metals, and it generally oxidizes them. I give you some of the reactions of HNO3. If you react copper with dilute HNO3, copper, 3 moles of copper plus 8 moles of HNO3 dilute will give you 3 moles of CuNO3, that is cupric nitrate, plus 2 moles of NO plus 4 moles of H2O. Whereas if you change it, if the HNO3 is not dilute, in fact it is concentrated, the product will be different. In that case, the reaction becomes Cu plus 4 moles of HNO3 concentrated. That will give you CuNO3 whole twice plus 2 moles of it. Now it will not give you NO, in fact it will give you NO2 plus 2 moles of H2O. Same type of reaction goes with zinc also. If you are reacting it with zinc, 4 moles of zinc will react with 10 moles of HNO3, that is dilute. It will give you 4 moles of Zn, NO3 whole twice plus 5 moles of H2O plus N2O. Likewise, if I am reacting it with the concentrated HNO3, so Zn plus 4 moles of HNO3, that is concentrated, I will get compound ZnNO3 whole twice plus 2 moles of H2O plus 2NO2. So these reactions, they are important. Reaction of HNO3 with zinc and copper in dilute and concentrated form. So you have to remember these reactions, otherwise rest of the reactions, they are quite easy. Like if you react HNO3 with the copper, with the carbon, it will convert it to CO2. It is a good oxidizing agent. So it oxidizes non-metals like carbon, nitrogen, phosphorus. So they undergo oxidation with HNO3. So this is all about the properties of HNO3. Here I would like to add one more thing. See, in the properties, you have to add one more thing, that is the ring test which you do for nitrate, detection of nitrate ion. You've done that in your practicals. Please do that. Otherwise, I'll add a video for that also. For practicals, when I'll be adding a video, I'll add the test for nitrate, and in that you'll get how to detect the presence of nitrate ring test. That again is a property of HNO3. So this is all about their oxo acids. After that, the last topic we are left with in 15th group is phosphine pH3, and we'll be talking about not only pH3 but also some chlorides like PCl3 and PCl5. That will not do in this video. We'll do that in the next video. So for this video, this is enough. Please do go through all these reactions. I'm telling you only the important reactions. So please do go through them. Thanks a lot. Thanks for watching. Do revise it. And in case you have not subscribed my channel, please do subscribe. This is how you support my efforts. Thank you very much.